Okay, so here we're back. We're looking at the 2016 AP Physics Free Response question, question number 2. This question is going to be dealing a lot with kinetic energy, collisions, and experimental design. So quickly read through the question. Okay, so now let's look at part A. Design an experiment to test the student's hypothesis about collisions of the ball with the hard surface. The student has an experiment. The student has equipment that would usually be found in the school physics laboratory. So basically what we need to know, the main thing we need to know in an elastic collision, kinetic energy is conserved. So what is kinetic energy? So kinetic energy is 1/2 mv squared. So we need to check whether the initial kinetic energy equals the final kinetic energy. Okay, so that means the quantity we need is velocity, v squared, and we need mass. So those are our two quantities, velocity and mass. And we can measure velocity in the experiment using a photo gauge. So that answers part 2. We need a photo gauge. And we need a scale for the mass. And part 3, I'm going to go through that verbally. So you're going to have to pay attention. So describe the procedure to be used to test the student's hypothesis. Give enough details so that another student could replicate the experiment. So what we're going to do is we need to figure out whether initial kinetic energy equals final kinetic energy. That'll tell us whether the collision is elastic or not. We're not going to be really using the conservation momentum equation because we just need to look at kinetic energy for elastic collisions because momentum will be conserved regardless. So describe the experiment. So what we're going to do is we're going to drop the ball from a certain height. That height should be kept constant. The height itself doesn't matter, just that it should be constant throughout all the trials you do. Do the trials 3 times. That's what we're going to do. We're going to drop it and we're going to place a photo gate at the top where it's dropped. We're going to place a photo gate on the floor right as it, so we're going to drop the ball. It's going to bounce off the ground. It's going to go back up. We'll get 2 velocity recordings, one on the bottom photo gate and one on the top photo gate. So the bottom photo gate will tell us the velocity it's coming down, and then the top photo gate will tell the velocity it's going up. So using those, we can find the initial kinetic energy and the final kinetic energy. So if they're equal to each other, then it's an elastic collision. If they're not equal to each other, then it is not an elastic collision. And that procedure can tell us whether the student's hypothesis is true. That's it for part A. Okay, so now let's take a look at part B. Describe how you represent the data in a graph or a table. Explain how that representation would be used to determine whether the data are consistent with the student's hypothesis. So the quantities we measured, the main ones, was kinetic energy. We measured kinetic energy. So what we're going to want to put in a table, we can have a table. That's our table right there. Wait, let's get rid of that first. So we can have our table right here. So obviously, since we're dealing with a collision, we're going to have before and we're going to have after. That's what we're looking at right now. So before, in that table, before is going to be our x-axis, after is going to be our y-axis. Sound good? So in our before, we're going to have kinetic energy, incident, or initial, and in our after, we're going to have kinetic energy. So this is a table that would represent that data basically, because we're trying to, for an elastic collision, we're looking at kinetic energy. We can look at momentum as well. So another method, another way to approach this would be initial momentum and final momentum. So that's another way to do it, but I'm mostly going to be dealing with kinetic energy, not momentum in this case, but it'll give you, the data can be represented the same way because in part A we looked at for mass and velocity, and that can be used in the momentum equations as well. But for now we're just going to look at kinetic energy. So explain how this representation would be used to determine whether the data is consistent. So just looking at the table alone, it would determine the consistent because this kinetic energy, the initial kinetic energy, let me write it out for you so it's more obvious. So the initial kinetic energy would not equal the final kinetic energy. That's what we're looking at there. That right there is what we are looking at. So that's how a table form could represent that. We could also look at a graph. So we can also look at a graph in the sense that, let me just delete this really quickly so we can look at something, so we can look at a graph. Okay, so our graph would look a little something like this. Kinetic energy here, incident, and then, so it would look like that. It looks like that because this is consistent with the student's hypothesis, because it would tail off at the end because kinetic energy is not considered. If kinetic energy. Okay, let's take a look at part C. A student carries out the experiment analysis described in parts A and B. The student immediately concludes that something went wrong in the experiment because the graph or table above shows behavior that is elastic for low speed, but appears to violate a basic principle for high-speed collisions. So give an example of a graph or table that indicates nearly elastic behavior for low-speed collisions, but appears to violate a basic physics principle. So for the nearly elastic behavior for low-speed collisions, we can simply use the graph that we had from part B. That's just going to go like that. It's going to tail out a bit just like that. Just like that. So now the next part is asking for violates a basic physics principle. So let's take a look at a basic principle. So one principle is conservation of energy, since we're dealing with an energy graph. So that means instead of conserving energy, would actually be adding energy. That would be a violation of a principle. Let's redraw that graph. That would be so would have energy and then suddenly would be adding more, just like that. Go like that. So that would violate a principle. So let's look at part 2. That's the graphical representation. So state one physics principle that appears to be violated in the graph that we just drew, and let's identify it. So that would be the conservation of energy. The conservation of energy. That's being violated. That's being violated right there. So that's being violated because the conservation of energy says the energy we have at the beginning will be the same as the energy we have at the end. If we're adding energy, then that would violate that principle. So that's part 2. So that's my interpretation of that's my solution to 2016 AP Physics 1. Question number 2.